Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Right now, as you listen to this, hundreds of miles above your head, there is a 1.6-ton national treasure that is it's slowly falling out of the sky.
Yeah, it's a completely surreal situation to watch unfold.
It really is. I mean, it's completely deaf to our commands right now.
Yeah.
Its scientific instruments have been purposely blinded, and it's just quietly plunging toward this fiery disintegration in the Earth's atmosphere.
Right, and usually, when the aerospace community discusses the end of a satellite's life, we're talking about a highly controlled deorbit burn.
Or pushing it into a graveyard trajectory, right?
Exactly, yeah. A planned retirement. But the situation currently unfolding in low Earth orbit, this is a crisis playing out in agonizing slow motion.
Agonizing is the word for it, because we are witnessing this ultimate high-stakes ticking clock.
We really are. You've got this multi-hundred-million-dollar piece of scientific infrastructure that is effectively drowning in the upper atmosphere.
Wow. Drowning. That's a terrifying way to put it.
Well, it's accurate. I mean, the most complex aspect of this entire scenario is the sheer physics of it. Once the atmospheric drag crosses a certain threshold, the mathematical reality of orbital mechanics just takes over.
You can't negotiate with gravity.
No, you really can't. And you can't simply hit a pause button to figure out your next move.
Which brings us to the actual urgency of this week, because this isn't, some theoretical problem for next year.
Definitely not.
Starting as early as this Tuesday. So literally right now in June 2026, an entirely unprecedented $30 million rescue operation is getting underway.
It's an incredibly audacious maneuver, honestly.
It's wild. A startup called Katalyst Space Technologies is launching a robotic lifesaver to catch this falling satellite, the Swift Observatory, before it crosses a very literal point of no return.
And just to put that in perspective, launching a fully autonomous machine into the orbital void to perform a high-speed interception of an uncooperative target. It's an act of absolute mechanical acrobatics.
Right. And we are going to break down for you every single mechanical, economic, and orbital factor of this operation today.
Because, 9 months ago, the consensus within the astrophysics and aerospace engineering communities was that this specific type of dynamic rescue was virtually impossible.
Not just hard, but actually impossible.
Yeah, virtually impossible within the given time frame.
So we're going to explore the mechanics of this crisis, starting with why a telescope that has been operating flawlessly since 2004 is suddenly plummeting.
Right. The physics of the fall itself.
Exactly. And then we'll examine the highly unorthodox design of the rescue robot, which I gotta say includes some engineering choices that seem almost primitive.
Primitive until you understand the brutal realities of the vacuum of space, yeah.
Yes. We'll get into that. We'll dissect the terrifying orbital ballet required to catch a fragile object moving at 5 miles per second.
5 miles per second. Just let that sink in.
It's unfathomable speed.
Oh.
And finally, we'll look at how this single desperate gamble might permanently rewrite the rules for humanity's entire footprint in space.
It's a huge paradigm shift.
But okay, before we get to the rescue, we need to understand the fall.
Right.
Why is a satellite that has been safely orbiting the Earth for over 20 years suddenly dropping like a stone?
So the primary catalyst here is not a mechanical failure aboard Swift itself.
It's not a broken part.
No, it hasn't suffered a catastrophic battery explosion, and it hasn't been peppered by micrometeoroids or orbital debris, nothing like that.
Okay, so what's pulling it down?
The culprit is actually 93 million miles away.
The sun.
Exactly.
Yeah.
We are currently experiencing a period of exceptionally violent solar activity.
Because we're at the peak of solar cycle 25 right now.
Right. The sun is erupting with intense solar flares and coronal mass ejections, just one after another.
And I know most people, they understand that low Earth orbit isn't perfect vacuum. There is a very thin trace atmosphere up there.
A very tenuous atmosphere, yes.
But what exactly is the mechanism connecting a solar flare to a satellite suddenly losing its altitude? How does a flash of light make a chunk of metal fall?
It comes down to extreme ultraviolet and X-ray radiation.
Okay.
When the sun releases a massive flare, it blasts the Earth with this enormous surge of highly energetic radiation.
Right.
And that solar energy slams directly into our upper atmosphere, specifically the thermosphere.
The thermosphere. Got it.
Right. And when you pump that much thermal energy into a gas, the molecules become highly excited.
Because heat is just movement, basically.
Exactly. They move faster, they push further apart, and the entire atmospheric layer physically expands outward.
Oh, wow. So the atmosphere actually swells. It puffs up.
Precisely. So picture Swift orbiting at what used to be a very comfortable, highly evacuated altitude.
Just coasting along in the quiet.
Yeah. But suddenly, because of this solar heating, the slightly denser layers of atmospheric gas that normally sit dozens of miles below Swift
Are pushed upward.
yes, push directly into the satellite's orbital path.
So a spacecraft zooming along at 17,000 miles an hour is suddenly hitting a much thicker wall of atomic oxygen and nitrogen.
And at orbital velocities, even a minuscule increase in atmospheric density creates a profound amount of aerodynamic drag.
It's like driving your car into a huge puddle on the highway.
That's a great analogy. The environment around the satellite effectively turns into a very thin quicksand.
Quicksand. Wow.
Every single molecule of oxygen that strikes the hull of the spacecraft robs it of a tiny, tiny fraction of its kinetic energy.
And speed is life up there.
Exactly. The fundamental rule of orbital mechanics is that your forward velocity is the only thing keeping you from falling back to Earth.
Because you're literally in free fall, you're just moving sideways fast enough to keep missing the ground.
Right, you're missing the Earth. But if friction bleeds your speed, you lose your altitude.
Yeah.
Gravity begins to win the tug of war.
Man. So let's quantify that fall, because the numbers here, they dictate this entire rescue timeline.
They absolutely do.
If we look at the orbital tracking data right now, Swift has sunk down to an altitude of 224 miles.
Which is roughly 360 kilometers, yeah.
Right. But the terrifying part is that this isn't a linear descent, is it? It's accelerating.
Right, the descent curve is compounding.
How does that work?
Well, as Swift loses altitude and sinks closer to the Earth, it enters even thicker layers of the atmosphere.
Because it's getting lower, so the air is denser.
Exactly. And that increased density creates even more aerodynamic drag.
Which bleeds its speed even faster.
Yes, causing it to drop into even thicker air. It is a vicious, self-reinforcing feedback loop of orbital decay.
Which establishes our hard deadline for this whole Katalyst mission.
The ticking clock.
Right. Because the absolute point of no return for this rescue is 185 miles. Or 300 kilometers.
Yeah, that invisible line in the sky.
If Swift drops below that line, the mission is over.
Completely over. Below 185 miles, the atmospheric drag becomes so severe that even if the rescue robot manages to catch Swift,
the robot's onboard thrusters won't be strong enough.
Right. They will not have enough thrust-to-weight ratio to overcome the friction and push the combined mass back up into a safe orbit.
So if they catch it too late, the robot just dies with it.
They would both be dragged down and burn up together.
Wow. And based on the current accelerating decay models, Swift is projected to hit that 185-mile death zone by October.
Which is just a few months away.
It's basically tomorrow in aerospace terms.
Oh, absolutely.
And that October deadline, that forced NASA to take some severe, arguably desperate measures earlier this year, right? Just to slow the bleeding?
Yes, back in February, NASA officially turned off all the scientific instruments on the Swift Observatory.
They completely ceased all astronomical observations.
Which is a huge deal for a science mission.
And I initially found this deeply confusing. I mean, how does sending a software command to power down a camera or an X-ray detector physically slow down the descent of a 1.6-ton metal cylinder?
It sounds counterintuitive, right?
Yeah. Turning off your car radio doesn't make your car more aerodynamic.
No, it doesn't. But in space, it has everything to do with attitude control and thermal management.
Okay, unpack that for me.
When the scientific instruments are powered on, the spacecraft has to constantly maneuver itself. It has to point those instruments at specific targets in deep space.
Right, it's constantly twisting and turning to look at things.
Exactly. Furthermore, the solar panels have to be articulated to face the sun to generate the immense amount of power required to run those detectors.
So it's presenting this very large, awkward physical profile to the direction of its travel.
Right. It's like running through water with your arms stretched out wide.
But by powering down all the instruments, NASA eliminated the need to generate maximum electricity.
Exactly. This allowed the flight controllers to use the spacecraft's reaction wheels to pivot the entire observatory into its most aerodynamically efficient posture.
They essentially took the large, flat solar panels and turned them edge-on into the wind of the orbital velocity vector.
Yeah, they feather the arrays.
Feathered them, like a diver tucking in their arms and pointing their toes to slip through the water with the absolute minimum amount of splash.
That's the perfect way to visualize it. That aerodynamic tuck severely reduced the cross-sectional area of the spacecraft that is plowing through those atmospheric particles.
So it doesn't stop the orbital decay?
No, you can't stop gravity.
But it drastically reduces the coefficient of drag.
Right, it buys them precious weeks on the clock.
Yeah.
It was a maneuver designed purely to stretch the timeline out to October, giving this rescue mission a fighting chance.
Which forces us to ask the foundational question of this entire endeavor, really.
Which is?
If Swift is 22 years old, built with early 2000s technology, and is currently just floating up there as an inert, powered-down brick,
why are we risking a brand new $30 million spacecraft to save it?
Exactly. Why not just accept the reality of solar maximum, let it burn up in a glorious streak of fire across the night sky, and launch a shiny, modernized replacement next year?
It's a fair question, but the economic and scientific realities make a simple replacement impossible.
How so?
First, from a purely budgetary standpoint, NASA does not have hundreds of millions of dollars just sitting in discretionary funds to design, build, test, and launch a bespoke replacement observatory.
Space is expensive.
It is incredibly expensive, but beyond the money, even if Congress wrote a blank check tomorrow, it takes a decade to develop a spacecraft of this caliber.
10 years.
At least. If we lose Swift today, we enter a massive decade-long dark age in high-energy astronomy.
Wow. Let's really analyze that irreplaceable capability we're talking about losing. Because Swift is not just a generic telescope staring at pretty galaxies, right?
Not at all.
True to its name, its entire architectural philosophy is built around speed. It is NASA's designated first responder for the most violent transient events in the universe.
Transient events being the key phrase there.
Right. What are we talking about when we say transient?
We were talking about gamma ray bursts, or the exact moment a massive star collapses into a supernova, or two neutron stars colliding.
The biggest explosions in the universe.
Yes. These events release more energy in a matter of seconds than our sun will emit over its entire 10 billion year lifespan.
That's staggering.
But the initial flash, the burst of high-energy radiation that contains the pure physics of the event, might only last a few milliseconds to a couple of minutes.
So if you are not looking exactly at the right coordinates at the exact millisecond it happens, the flash is gone forever.
Exactly. You miss the fingerprint of creation.
And Swift was engineered to solve that exact problem.
Right. Its burst alert telescope constantly monitors a massive swath of the sky.
Just waiting.
The moment it detects a spike in high-energy photons, the onboard autonomous software instantly calculates the coordinates of the burst.
Instantly.
Yes. Then, using its heavy reaction wheels, Swift physically slews the entire spacecraft, violently pivoting in orbit to point its higher-resolution X-ray and ultraviolet telescopes directly at the source.
Catching the fading afterglow.
Catching it right as it happens.
But the true magic of Swift isn't just that it looks at the explosion itself.
No, it operates as the central nervous system for the entire global astronomical community.
It is the ultimate celestial dispatcher.
That's exactly what it is. Within seconds of detecting a gamma-ray burst, Swift transmits those exact celestial coordinates down to Earth through the TDRS relay satellite network.
Right, the tracking and data relay satellites.
And those coordinates are immediately blasted out to ground-based observatories all over the world.
Everyone turns their telescopes.
Everyone. And more importantly, to other assets in space.
Assets like the James Webb Space Telescope.
Yes, and the soon-to-launch Roman Space Telescope.
Right.
These flagship observatories are engineering marvels with unprecedented resolution, but they have extremely narrow fields of view.
Because they're designed to look deep, not wide.
Exactly. They're essentially looking at the universe through a soda straw.
A very expensive soda straw.
Very expensive. They cannot search the sky for random millisecond flashes. They need Swift to act as the wide-angle security camera that detects the motion, taps them on the shoulder, and says, look at these exact coordinates right now.
Point your soda straw over here.
Exactly.
So if Swift burns up in the atmosphere this October, Webb and Roman are fundamentally compromised.
They lose their trigger mechanism.
As NASA's science mission chief, Nikki Fox, bluntly stated, if Swift re-enters, we lose a massive swath of our observational capability.
They are wandering the universe with blinders on.
Wow. Which highlights a critical, often misunderstood concept in orbital architecture, doesn't it? The profound value of legacy hardware.
It's so true. On Earth, we are conditioned by the consumer tech cycle to view 20-year-old electronics as obsolete garbage.
Right, like a laptop from 2004 is basically a paperweight.
Exactly. But in the realm of astrodynamics and space infrastructure, a satellite from 2004 that is still operational is a marvel of over-engineering and endurance.
It's a load-bearing pillar. You don't demolish a 20-year-old foundation just because it's old, especially when the brand new $10 billion roof of the James Webb Space Telescope is resting entirely on top of it.
You reinforce the pillar.
You reinforce it. Which brings us to the actual mechanics of the rescue.
The hard part.
The incredibly hard part.
Yeah.
The astrophysics director at NASA, Sean Donegal-Goldman, acknowledged that a dynamic orbital intercept of this nature was considered outside the realm of possibility just a short time ago.
Yeah, the physics of matching orbits, approaching an uncooperative target, and securing it without causing a catastrophic collision, it requires a level of autonomous precision that we simply haven't fielded before.
So enter Katalyst Space Technologies, the startup attempting to do the impossible this week.
Right.
Their CEO, Gan-hee Lee, has overseen the development of this autonomous rescue robot named Link.
Link.
And we need to dissect the physical anatomy of Link because its engineering is deeply fascinating.
It really is.
Specifically because it abandons complex sci-fi aesthetics for this brutal functional pragmatism.
To understand how Link operates, you really have to visualize its scale first.
Okay, paint the picture for us.
The main body of the spacecraft is relatively compact, roughly the dimensions of a standard kitchen refrigerator.
Okay, a flying fridge.
Right. And that fridge houses the propellant tanks, the autonomous navigation computers, the star trackers, and the communication arrays.
The brains in the gas tank.
Basically.
Yeah.
But from that central refrigerator body, it deploys these massive solar wings spanning 40 feet or about 12 meters across.
40 feet. That's huge compared to the fridge part.
It needs to gather a tremendous amount of power for the orbital transfer burns.
Okay, that makes sense. But the most striking design choice, however, and the one that initially made me highly skeptical of this $30 million mission, is its robotic arms.
Ah, the grapple mechanism.
Yes. Link has 3 arms, each extending just over 3 feet, or about a meter, from the main body.
Right.
And at the end of each arm, there is no sophisticated, multi-jointed robotic hand. There are no highly dexterous fingers. Instead, there are simple, 2-pronged pinching grippers. They look remarkably like the hands of a standard Lego minifigure.
It's essentially a simple C-clamp design.
A C-clamp. I have to push back on this. If you are executing a historic, high-stakes space rescue, relying on a primitive C-clamp feels like an absurd risk.
I get why you'd think that.
Right. Why not use a robotic hand with high-fidelity dexterity to ensure they can delicately navigate around Swift's fragile solar panels?
Because your instinct to want dexterity is completely logical on Earth. But in the vacuum of space, complexity is the enemy of reliability.
Complexity is the enemy, okay.
Think about a highly articulated robotic hand with dozens of microjoints, tendons, and actuators.
Like a human hand.
Yeah. Up there, that represents dozens of single points of failure. Consider the thermal environment of low Earth orbit.
The temperature swings.
Exactly. When Link is in direct sunlight, the surface temperature of those arms will spike to over 250 degrees Fahrenheit.
Boiling.
Beyond boiling. And then 45 minutes later, when it passes into the Earth's shadow, the temperature plummets to minus 250 degrees.
So the metals and joints are constantly expanding and contracting.
Violently expanding and contracting. If you have intricate, tight tolerance joints in a humanoid robotic hand, that thermal cycling will almost certainly cause the mechanism to bind or seize entirely.
It would just lock up.
Completely.
Oh.
Furthermore, in a hard vacuum, you have to worry about a phenomenon called vacuum welding, or cold welding.
Cold welding, where 2 metals touch and fuse together?
Yes, because there is no atmosphere to create an oxidation layer on the metal surfaces. If 2 pieces of similar bare metal scrape against each other in the hinges of a robotic finger,
they can't tell they're separate pieces anymore.
Exactly. Their atoms can literally fail to recognize the boundary between them. They fuse into a single solid piece of metal.
A completely jammed hand.
Exactly. So Katalyst engineers opted for the Lego hand C-clamp.
Keep it simple, stupid, basically.
It requires only a single, heavily shielded actuator to pinch the 2 prongs together. It is robust, it is thermally resilient, and it provides a massive high-torque grip, without the fragility of articulated fingers.
So it's actually a masterpiece of pragmatic mechanical engineering.
It really is. It's brilliant in its simplicity.
It's the ultimate expression of function over form. I mean, visualize this. A flying smart fridge with 40-foot wings and 3 giant Lego hands, tasked with catching a spinning, multi-million-dollar telescope.
It sounds like science fiction, but it's happening.
And getting this bizarre machine into the orbital corridor is a story in itself because Katalyst is utilizing a highly unorthodox launch method.
Right, they aren't using a standard rocket.
They are not rolling a massive rocket out to a concrete pad at Cape Canaveral or Vandenberg Space Force Base.
No, the launch architecture is vastly different. Link is being launched from an atoll in the Marshall Islands, located in the Central Pacific Ocean.
Okay.
But it's not lifting off from the ground.
Wait, what do you mean?
Link is encapsulated inside the fairing of a Pegasus XL rocket. That entire rocket is then mounted horizontally underneath the belly of a heavily modified carrier airplane.
So an airplane takes off with a rocket strapped to its stomach.
Exactly. The airplane takes off like a standard commercial flight, climbs to an altitude of roughly 40,000 feet over the open ocean, and literally drops the rocket.
Just drops it out of the sky.
Drops it. The Pegasus falls in free fall for about 5 seconds to clear the aircraft, ignites its first stage solid rocket motor in midair, and blasts its way into low Earth orbit.
That is insane, and that is not merely a party trick, right?
Oh, not at all. Launching from the belly of an aircraft provides an overwhelming strategic and mathematical advantage for a rapid response orbital intercept mission.
How? Because it seems so complicated.
Well, if you launch from a static concrete pad in Florida, you are geographically bound. You have to wait for the rotation of the Earth to carry your launch pad precisely under the orbital plane of the target satellite.
So you have to time it perfectly.
And if you miss that launch window by even a few minutes, the orbital math fails.
Utterly fails.
Yes. Once you are in space, changing your orbital inclination, meaning tilting the angle of your orbit relative to the equator, requires a massive, prohibitive expenditure of propellant.
Because you're trying to turn while going 17,000 miles an hour.
The physics of shifting your velocity vector sideways at that speed is brutal. If Link used all its fuel just trying to align its plane with Swift after a ground launch, it wouldn't have enough fuel left to actually push Swift back up to a higher altitude.
So the airplane solves the inclination problem before the rocket even ignites.
It allows us to transition from a geographically bound space program to a geometry-bound space program.
A geometry-bound space program, that is a phenomenal paradigm shift.
It really is. The carrier aircraft operates as a fully mobile launch pad. They fly the plane to the exact latitude, longitude, and heading required to perfectly match Swift's specific decaying orbital plane.
So they just line it up in the atmosphere.
Right. The Pegasus rocket fires directly into the correct geometric corridor, ensuring that Link arrives in orbit with nearly full propellant tanks, ready for the heavy lifting.
Ready to do the actual job.
Exactly.
But getting Link inserted into the correct orbital plane is merely the preamble, isn't it?
Oh, yeah. That's just the commute.
The actual rendezvous and docking, the moment those Lego hands have to make physical contact with the observatory, is where the tension reaches a terrifying peak.
The timeline itself illustrates the agonizing precision required here. It will take Link an entire month just to execute the rendezvous phase.
Wait, a full month?
Yes, 30 days.
Why does it take 30 days to catch something if you launched into the correct orbital plane? I mean, why not just burn the engines and fly straight toward it?
Because orbital mechanics do not function like atmospheric flight. You can't just aim and hit the gas.
Okay, explain that.
Link will be placed into a slightly lower phasing orbit beneath Swift.
Let's visualize this. Think of it like 2 race cars on a massive circular track. If Swift is in the outer lane and Link is in the inner lane, Link is naturally going to travel around the track faster because the circumference of the inner lane is shorter.
That is an excellent analogy. Yes. Link uses that lower, faster inner lane to gradually catch up to Swift's position over the course of weeks.
Slowly closing the gap.
Right. Yeah. As it approaches from behind and below, Link will execute a series of incredibly precise, computer-controlled engine burns to slowly raise its altitude, moving from the inner lane to the outer lane.
And as it moves up to the outer lane, its speed naturally decreases to perfectly match Swift's speed at the exact moment their orbits intersect.
If the math is perfect, yes.
Big if.
Very big if. But once they're occupying the same space, moving at identical velocities, the true nightmare of this mission begins.
The catch.
The catch. Because Swift was manufactured in the early 2000s. It was absolutely never designed to be repaired, serviced, or physically grappled by another spacecraft.
It has no docking ring.
None.
It has no structural handles painted with high-visibility arrows.
Nothing like that.
It is a delicate scientific instrument covered in extremely fragile multi-layer thermal insulation and highly sensitive optical sensors.
It's basically a giant fragile glass eye covered in foil. Which brings us to the two non-negotiable golden rules NASA established when they awarded Katalyst this $30 million contract last September.
Okay, what are the rules?
Rule number 1, execute this fast, because the aerodynamic drag is pulling the target into the death zone.
The ticking clock to October.
Right. Rule number 2, under no circumstances are you allowed to make the situation worse.
Don't make things worse.
Which sounds incredibly simple on Earth.
Right, like just don't drop it. But in space, when dealing with kinetic energy, one tiny mistake is lethal.
Lethal is the correct word. We have to consider the relative velocities here. Both Link and Swift are hurtling through the thermosphere at 5 miles per second.
5 miles per second, that's over 17,000 miles an hour.
Now, relative to each other, Link's autonomous navigation systems will use LiDAR and optical cameras to bring that speed difference down to mere inches per second during the final approach.
So they're both going insanely fast, but relative to each other, they're just creeping along.
Exactly.
Yeah.
But the total kinetic energy of a 1.6-ton object is immense.
Right, the mass doesn't disappear.
No, it doesn't. So if Link's targeting algorithms miscalculate by a fraction of an inch,
Oh, man.
if one of those anodized aluminum Lego hands bumps the side of Swift on a glancing angle, instead of securing a firm structural hardpoint like the Marmon clamp ring.
It transfers that kinetic energy into rotational momentum.
Exactly. It would impart a torque to the observatory.
It would push it.
And because Swift is fully powered down, its reaction wheels are offline. It has zero attitude control authority.
It can't stabilize itself.
It cannot fight back against that imparted spin.
So it would start tumbling end over end.
And if it begins to tumble, the mission instantly ends in failure.
Why instantly?
Because a tumbling cylindrical spacecraft presents a massive, constantly shifting cross-sectional area to the atmosphere.
Like we talked about earlier, it wouldn't be aerodynamic anymore.
Exactly. The aerodynamic drag would triple or quadruple instantly. The rate of orbital decay would accelerate exponentially, and Swift would quickly plunge into the thicker atmosphere and vaporize.
Wow. That is what "don't make things worse" means. A simple bump condemns the telescope to immediate destruction.
The stakes are astronomical. There is absolutely zero guarantee of success here.
Katalyst and NASA are literally rolling a $30 million pair of dice in the dark, utilizing untested autonomous docking algorithms and C-clamp hands.
But they're forced to take the gamble.
Because the alternative doing nothing guarantees the loss of our primary gamma-ray sentinel.
It is the ultimate, uncompromising test of autonomous robotic capability. There are no joysticks on Earth controlling Link during those final minutes.
Really? Nobody's flying it.
No, the time delay in communications means Link's onboard computers must analyze the geometry, calculate the vectors, and execute the grapple entirely on their own, millions of feet away from human intervention.
It's all up to the robot.
Entirely.
But this is where the narrative expands beyond the survival of a single observatory.
Right, the bigger picture.
Because if Katalyst actually pulls off this Lego-handed miracle, if they manage to gently secure Swift and spend 2 months firing their thrusters to drag that 1.6-ton mass out of the 224-mile danger zone and up to the safe haven orbit of 373 miles.
This is the goal.
It fundamentally shatters the paradigm of how humanity operates in space.
It really does. It rewrites a doctrine that has governed aerospace engineering since the launch of Sputnik in 1957.
70 years of history.
For nearly 70 years, our entire orbital architecture has been defined by a throwaway culture.
Throwaway culture. Yeah.
Think about it. Space agencies and private corporations spend hundreds of millions of dollars to build exquisite, highly capable machines. They launch them into the void, and the moment a single component fails,
A reaction wheel seizes, a coolant valve sticks, or the propellant tank runs dry.
that multi-million-dollar asset instantly becomes useless orbital debris.
We just abandon them to the dark.
Completely. We write off the loss and spend another decade building a replacement from scratch.
But if Link succeeds this week, It violently disrupts that economic model.
It proves that in-orbit servicing, repair, and relocation are not just whiteboard concepts for a distant future.
It proves they are viable commercial realities today.
Right now.
Although, to maintain absolute historical accuracy, we should note that the United States is not the first nation to attempt manipulating an object in orbit.
No, it's true. The Chinese Fix program executed a somewhat similar maneuver roughly 4 years ago, where one of their orbital tugs successfully grappled a defunct, dead satellite and boosted it higher into a graveyard orbit.
Right. But that is a critical distinction, though.
It is. Pushing a piece of dead, inert debris out of a crowded orbital lane is an impressive feat of navigation, absolutely. But it is effectively cosmic janitorial work.
Cleaning up space junk.
Right. What Katalyst is attempting with Link is fundamentally different. They are attempting to delicately grapple a highly fragile, currently operational scientific instrument, specifically to preserve its functionality and return it to active duty.
It's the difference between towing a totaled car to the junkyard and performing open-heart surgery on a patient in the back of a moving ambulance.
That is precisely what it is. And establishing this capability right now couldn't possibly be more urgent because Swift is not an isolated anomaly.
No, it's not. It is simply the canary in the coal mine.
Exactly.
This is the realization that elevates this entire situation from an interesting technical challenge into a systemic crisis.
The solar maximum affects everything.
Swift is not the only national treasure getting dragged down by the expanding thermosphere. The exact same extreme ultraviolet radiation is currently pulling down the Hubble Space Telescope.
Hubble, arguably the most famous scientific instrument in human history.
Everyone knows Hubble.
It is 36 years old.
Yeah.
It revolutionized our understanding of astrophysics, definitively proving the expansion rate of the universe and capturing the first light of ancient galaxies.
But it's fundamentally subject to the same aerodynamic laws as Swift. The atmospheric quicksand is rising, and Hubble is sinking.
And the tragic irony of Hubble is its history.
What do you mean?
Hubble was specifically designed to be touched.
Oh, right. The shuttle missions.
During the space shuttle era, NASA flew 5 separate servicing missions to the telescope. We sent spacewalking astronauts up there to manually install corrective optics, replace failing gyroscopes, and upgrade its cameras.
It was built with modular bays and massive yellow handrails specifically for humans to grab onto.
But that human capability no longer exists.
The space shuttle fleet was retired over a decade ago.
Right. And currently, there is no crewed spacecraft in the American inventory. Not the SpaceX Crew Dragon. Not the Boeing Starliner that possesses the necessary airlocks, robotic arms, and payload capacity to safely transport astronauts up to Hubble's specific altitude.
Not to mention allowing them to execute complex spacewalks to repair and boost the observatory and return them safely to Earth.
So Hubble is entirely stranded.
It was stranded until the development of autonomous systems like Link.
Right, this is where it all connects. Katalyst Space Technologies is already heavily analyzing a 2028 rescue architecture for Hubble.
2028, just 2 years from now.
They are designing a next-generation, larger robotic servicing vehicle, iterating directly on the flight data and autonomous algorithms they intend to prove this week with Link to execute a life-extending orbital boost for the Space Telescope.
Man. If they can successfully save Hubble, an asset that represents an incalculable scientific value to humanity, the economic leverage is staggering.
It really is. You are preserving billions of dollars of astronomical capability for a fraction of the cost and a fraction of the time required to build a successor.
But the vision of Katalyst CEO Gan-hee Lee extends far beyond rescuing aging telescopes in low Earth orbit.
He is looking at a roadmap for next year, 2027, that scales this autonomous robotic architecture out to 22,300 miles.
Geostationary orbit.
Yes.
That is the realm of the absolute leviathans of the aerospace industry. The massive school bus-sized telecommunications relays, the global weather satellites, the multi-billion-dollar military early warning arrays.
Gan-hee Lee envisions deploying fleets, hundreds of these autonomous Lego-handed robots throughout the orbital corridors.
So we are rapidly moving past the concept of a celestial tow truck service.
This technology unlocks the foundation of a true in-orbit economy.
An in-orbit economy. What does that actually look like?
We are talking about deploying robotic tankers to autonomously refuel massive communication satellites, extending their profit-generating lifespans by decades.
Just pulling up and gassing them up.
Exactly. We are talking about in-orbit assembly.
Building things in space.
Yes. Once you have robots capable of delicate high-precision manipulation in a vacuum, You no longer have to build your entire spacecraft on Earth.
Right.
You can launch raw materials, modular struts, and solar panels, and have a team of autonomous machines assemble them in orbit.
Wow.
You can build space-based solar power farms measuring miles across that beam continuous microwave energy back to the terrestrial grid.
Miles across.
You can construct massive orbital data centers utilizing the ambient cold of space for cooling and limitless solar energy for power.
It completely sidesteps the most punishing bottleneck in aerospace engineering, doesn't it? The fairing size of the launch vehicle.
Oh, absolutely. The tyranny of the fairing.
Right now, if you want to put a telescope in space, it has to fold up like complex origami just to fit inside the nose cone of a rocket.
And it has to be built robustly enough to survive the violent acoustic vibrations of the launch.
But with in-orbit assembly, it's like shipping flat-pack furniture to space.
Exactly. IKEA in space.
You send up the dense, heavy boxes of parts, and the robotic assemblers snap it all together in zero gravity.
It removes the gravity well as the primary constraint on human engineering. If we can maintain the assets we already have in orbit and autonomously construct unprecedentedly large structures directly in the vacuum, we exponentially multiply humanity's capacity to operate in space.
So, bringing all of this profound orbital mechanics and economic theory back down to the immediate reality.
Tuesday's launch.
Right. What we are watching this week as that Pegasus rocket drops from the belly of a carrier aircraft over the Pacific Ocean is not merely a desperate $30 million gamble to save a single 22-year-old telescope.
No, we are watching a stress test for the future of orbital infrastructure. The success or failure of Link C clamp hands will determine the viability of a sustainable, repairable ecosystem in space.
It is the absolute bleeding edge of humanity's transition from a throwaway culture to a civilization capable of persistent orbital industry.
It really is.
And it leaves you with a deeply provocative angle to ponder as you watch this mission unfold.
What's that?
Well, for the entire history of the space age, we have viewed outer space as a pristine, utterly untouchable void.
A frontier.
It has been a silent, harsh frontier where our machines are launched to do their work, and inevitably where they are left to die alone in the cold.
It has always been a graveyard.
But if Link works, if we successfully deploy autonomous robots to catch falling telescopes, refuel aging satellites, and assemble massive solar farms and data centers 22,000 miles above the Earth,
Everything changes.
at what point does outer space cease to be a vast romantic frontier and simply become a heavily industrialized suburb of Earth?
That is a fascinating way to look at it.
Think about how profoundly that alters our fundamental relationship with the cosmos. The next time you walk outside and look up at the night sky, you aren't just looking into an empty void.
No.
You might be looking at the faint, rapidly descending streak of a 1.6-ton national treasure and the tiny robotic hands reaching out into the absolute dark to catch it.